Right, this is part 7 of chemistry. We're taking a look at a specific type of protein, enzymes. So enzymes are proteins that speed up a metabolic reaction. I'm taking a little bit of liberty here and just saying all enzymes are proteins. It's not entirely true. A more correct definition would be organic catalysts, because there are some RNA molecules that show catalytic activity, but even they have proteins. So for simplification, we're just going to say enzymes are proteins, and they speed up metabolic reactions. And these metabolic reactions consist of bond breaking and or bond formation. And so in order for the reaction to proceed, we're going to need to break those bonds. And so these metabolic reactions are going to have an energy barrier, that some amount of energy, an input of energy, is going to be needed to break these bonds and allow the reaction to occur. And that initial energy investment is called the energy of activation. And so on the next slide, I'm going to kind of draw this stuff out. So if we have, let's say, a hypothetical A bound to B plus C bound to D, and let's just make this a double displacement. So before this reaction can proceed, I'm going to have to break the bond between A and B and C and D. And so that energy that is required to do that so the reaction can proceed is that energy of activation. And so if we graph this, and I graph some sort of energy versus the progress of the reaction. And I'm just going to arbitrarily pick a point. And for simplicity's sake, we're going to say that both our reactants possess the same amount of energy. So what the energy of activation says is that as the reaction proceeds, we're going to have this input of energy. And it really doesn't matter where this ends. It can be up here, it can be down here. But this spot right here is our energy of activation. And just to complete this. And so what enzymes do is they lower our energy of activation. So if I do a dotted line now for where my new energy of activation is going to be, this dotted line is when I add enzymes. So now these guys only have to possess this much energy instead of this much energy. So the reaction is going to proceed that much quicker. And you'll see that on this next slide. Normally I'd say my drawing is better, but with this computer setup, probably not. So here's the energy of activation without enzymes. Once we add enzymes, we lower that energy of activation. So it's going to be that much quicker for our reactants here and here to obtain this much energy as opposed to this much. Okay. So that is a big take-home message here is how do enzymes work? They work by they lower energy of activation. And so these metabolic reactions that occur in our body, they all need enzymes. And that's why it's so critical that you guys understand just some of the basics behind enzyme activity. And just some nomenclature associated with enzymes. We have a substrate, and that's just the substance that the enzyme acts on. And the active site is a shallow depression or groove on the enzyme where the substrate binds. So I'm going to try and draw again. So let's say we have sucrose. Hopefully you guys remember what sucrose is made up of. Glucose and fructose. And the enzyme that catalyzes that is sucrase. Most enzymes will end in ASE. Of course, not all of them. But if you ever come across a term that ends in ASE, it will be an enzyme. So if we take a look at this, here is my sucrose molecule. I mean, it really doesn't look like this. And here is my sucrase. And so these guys are going to meet by random collision. They're going to form this temporary enzyme substrate complex before releasing the products. There's glucose. And we'll say this is fructose. And the enzyme is left unchanged. So one enzyme can catalyze the same reaction over and over and over again. Okay? And that's what this is showing. All right, so this is the active site of the enzyme. Keep in mind, the active site is on the enzyme. The substrate fits. Kind of another way to think of it is think of the substrate as the key. The enzyme is kind of like the doorknob, and the active site is the keyhole. So this is, since this is a protein, it has a tertiary structure. And so the shape of this active site will only allow for that one substrate to fit. Right? Let me back up for a second. If I added maltose to a test tube with sucrase, sucrase would not be able to break down maltose into glucose and glucose because maltose would be shaped like that. So it wouldn't be able to fit into that active site. So because enzymes are proteins, that gives them such a high specificity. Please let me back up. All right, sorry about that. One last thing with enzymes. So regulating enzymes is really, really important because all it takes is just one enzyme to catalyze a reaction over and over and over again. And a lot of pathologies result when the body can no longer regulate enzymes. The other thing that can happen is that enzymes can be what are called denatured. Excessive temperatures can cause the protein or the enzyme to unfold. So if I took a test tube with equal amounts of enzyme and substrate and I boiled it, I would get no activity. Because the temperature, in this case, would affect the enzyme's structure, and instead of the enzyme looking like this, it would be completely unfolded. Okay. Antibiotics, about half of antibiotics will also change the shape of enzymes that are found in bacteria. Right. So those are just some quick additions here. Kind of related to your field, right? Antibiotics, most of them will either inhibit protein synthesis or they will bind to the enzyme, changing its shape and making it inactive because there is no such thing as life without enzymes. All right. And so now this is the end of the recording.